Year 13, Chapter 10, Integration Lesson 10, Exam Questions. In this lesson, we're going to have a look at a range of different questions involving the full range of integration techniques that you have been learning about. So let's take a look at the first example. It's a trigonometric integral. Now, this is a standard result. We can integrate this using inspection. We could integrate this using integration by substitution and setting up u equal to 3x, but it's much simpler if we can just do this directly. So we know that sine integrates to negative cos, so this will integrate to negative cos 3x, but of course we need to divide by the derivative of the inner function, so we want negative 1/3 cos 3x. And you can always check by thinking, does it differentiate back to being sine 3x? And yes, it would. So here are our limits, 0 and pi by 6, and let's substitute these in. So we get negative 1/3 cos 3 pi by 6 minus negative 1/3 cos 0. So what does this give us? 0, and then we have plus 1/3. So the answer is simply 1/3. Okay, so we have another integral. Now I'm going to write this so we can see the power function clearly. So it's 3x minus 2 to the power of negative 1/2. Again, we could do this with substitution, setting up u equals 3x minus 2 and following through the whole process, but we can also do this by inspection because we have a linear function here being raised to a power. So it's going to integrate in the following way. We raise the power by 1, so the new power is 1/2. We divide by the new power. Now, dividing by 1/2 is the same as multiplying by 2. And we need to make sure we divide by the derivative of this inner function, which is 3. So we have a 2/3 here. And then, of course, we need to input our limits 1 and 2. Now, a simpler way of doing this is to take the 2/3 out as a common factor and then input the limits here and here into this part, and then just make sure that everything is multiplied by 2/3 at the end. So inputting the upper limit of 2 gives me 4 to the power of 1/2, and inputting the lower limit of 1 gives me 1 to the power of 1/2. So my final answer is simply 2/3. So in this question, we're told to use a suitable substitution or otherwise. Now that's usually quite a broad hint that we need to do this in a particular way. So we're going to look for a substitution, and it's usually, but not always, the denominator. So u equals 3 plus cos 2x. So du by dx, if we differentiate that, gives me negative 2 sine 2x. Effectively using the chain rule to differentiate, but really I'm using the quick chain rule, illustrating how important it is to make sure you can use the chain rule efficiently and differentiate standard results. We then have our sort of fake rearrangement. So this gives me this, and we'll then be ready to start the substitution. So this integral then becomes the integral of, now I'll leave sine 2x in the numerator for the moment. The denominator is then u, and in place of dx we have this. Now we need to make sure we change our limits so that they're not in terms of x. These limits here are in terms of x, and we need to convert to u. So let's do that next. So if x is equal to 0, then u equals 3 plus cos of 0. Remember, I'm using this to convert the limits. So that gives me a limit of 4. So the lower limit is 4. And if x is equal to 1/2 of pi, then u is equal to 3 plus cos pi, which gives me an upper limit of 2, as cos of pi is -1. So notice my upper limit is lower than my lower limit. But because I have a negative sign here, I can switch the limits and then negate the integral, which effectively gets rid of the negative sign. So I then end up with this. Remember, we're going to get a nice cancellation of sine 2x here. I'm going to pull the factor of a half out of the front of the integral, and then I'm left with 1 over u du. Remember that negative vanishes because we've switched the order of the limits. So I then integrate, so I have a half and then ln mod u. I must include the modulus until I know that it's no longer needed. So this then gives me a half ln 4 subtract ln 2, and ln 4 subtract ln 2 is the same as ln 4 over 2 using our logarithm rules, so that is a half ln 2, which is the expected result. So let's take a look at this integral here. Now we can see there's a clear product, and integration by substitution isn't going to work here because one part of this is not going to differentiate to another part of this. So we're going to have to do this using integration by parts. So I want to make sure that we remember the integration by parts formula, so let's write that down. So remember, we want to choose our u and our dv by dx very carefully. We want to choose the trigonometric function, ideally, for dv by dx, and we want to choose u to be x. So du by dx is then 1, so this is u, and this is dv by dx. So dv by dx is cos a half x, so integrating that then gives me v equals. Now, integrating a cos function becomes a sine function, so sine of a half x, but I need to divide by the derivative of this inner function, and dividing by a half gives me a multiple of 2. So there we have the components. So let's put together our result. So the integral of x cos a half x dx between 0 and pi by 2 is equal to uv first of all. So that is x multiplied by 2 sine a half x. And of course we need to make sure we put the limits of 0 and pi by 2 in at some point. And then we're subtracting from that the integral of v, which is 2 sine a half x multiplied by du by dx, which is 1, and that's being integrated with respect to x. Okay, so I might put the limits in at this point here. So that's 2 times pi by 2, and then sine pi by 4, and then my lower limit will just give me 0 because when it's substituted in for x here, we just get a 0. We then have subtract 2, and then integrating this part here, this sine a half x. Sine integrates to negative cosine, so we get negative cos a half x, but we need to divide by the derivative of the inner function here. The derivative of a half x is a half, dividing by a half is the same as multiplying by 2, so we need that there. And of course we need our limits of 0 and pi by 2. So over here, evaluating this bracket here, sine pi by 2 is root 2 over 2. So we get pi multiplied by root 2 over 2, which, if we notice, is part of the answer up over here. So that's promising. So just need to check that we get the rest of this correct. Now, there is a minus, you can see the blue sign, and a minus, you can see the purple sign, and a 2 multiplied by 2. So I'm going to combine those, so we get plus 4. And then we need cos of pi by 4 minus cos of 0, substituting in the limits. So this then simplifies. Now cos of pi by 4 is root 2 over 2. Multiply that by 4 and we'll get the 2 root 2. cos of 0 is 1, and of course we then multiply by 4 outside the bracket. So we get the desired answer. So we now move on to a much more detailed question. Let's take a look at this carefully. So we have a curve and a straight line. Now we don't know the full equation of the straight line. We only know that its equation is y equals mx, and the gradient is between 0 and 1. So part 1, show that the x-coordinate of P is this. Now, notice that the answer we're aiming to get to contains m, which means at this moment we're not actually looking to find the value of m. So, part 1, we know at point P there is an intersection between the line y equals mx and the curve xe to the negative 2x. Now, I'm then going to take everything over to one side like this, and then factorise. Now, if x equals 0, this is not P, this is what's happening at the origin, because there are 2 points of intersection between the curve and the straight line. So we're not looking for that solution there. We're looking for this one here. So this one, m minus e to the negative 2x equals 0, e to the negative 2x equals m. Take ln of both sides, so negative 2x equals ln of m, and x then equals negative 1/2 ln of m, which is the required result. Now, part 2. Find in terms of m the gradient of the tangent to the curve at P. So, the gradient of the tangent would look like this. You can see, actually, they've drawn some of it with that dotted line there. So we need to differentiate the equation of the curve. So y equals xe to the minus 2x. We're going to need to use the product rule to differentiate this. So this is where you've got to be really comfortable at switching between integration, differentiation, the range of techniques. So u equals x and v equals e to the negative 2x. du by dx is equal to 1. And dv by dx is equal to negative 2e to the negative 2x. Again, you're using the chain rule there, but you're going to have to use it very quickly and efficiently. Then dy by dx is equal to u multiplied by dv by dx plus v multiplied by du by dx. So let's put all the pieces of information together. U multiplied by dv by dx first gives us negative 2x e to the negative 2x. And then the other way around, v multiplied by du by dx gives us e to the negative 2x. Now, at P, we know the x-coordinate is negative 1/2 ln m. And we have to substitute that in for x in the gradient formula. So dy by dx is then equal to negative 2 multiplied by negative 1/2 ln m, e to the negative 2 multiplied by negative 1/2 ln m, plus e to the negative 2 multiplied by negative 1/2 ln m. And there are lots of different ways of working through the full substitution. I've perhaps done more working than you might need to here, just to make the point really clear. So let's simplify this. And we can see that we're going to get ln m from here. Now we're then going to get e to the power of ln m, which will simplify to just give us m, and the same over here. So our final answer is going to be m ln m plus an m. So let's take a look at part 3 of our question now. So we are given that OP and this tangent are equally inclined to the x-axis. So show that m is equal to e to the negative 2. So we know that the gradient of the tangent, which I'll just draw on again, roughly this line here, was equal to m multiplied by ln of m plus an m. And we know that the gradient of this line is m. Now, what we know is that they have equal inclination to the x-axis, which means if the green gradient was equal to 2, then the yellow gradient would be equal to -2. If the green line had a gradient of 5, then the yellow dotted line would have a gradient of -5. So they are gradients of the same magnitude, but they are the negative of each other. So I can say that m is equal to negative m ln m plus m. So where can I go from here? So m is equal to negative m ln m minus m. Add m to both sides, so we get 2m equals negative m ln m. Now, because we know m is not equal to 0, we can divide through by it. So that gives me 2 equals negative ln of m. Divide both sides by -1, so -2 equals ln of m. E to the -2 then equals m, or m equals e to the -2. Now, to find the exact coordinates of P, so at P, we know that x is equal to -1/2 ln of m. We're given that information up over here. M we can now replace with e to the -2, so that's -1/2 ln e to the -2. ln of e to the -2 gives us -2, so this is -1/2 multiplied by -2, which is 1. So the x-coordinate of P is 1. Y is then equal to mx at P, because it's on that line. It's the easiest way of finding. It's easier to substitute into this than into the equation of the curve. M we know is e to the -2, and x is 1, so y is e to the -2. So the coordinates of P are 1 and e to the -2. Now, part 4 of this question asks us to find the exact area of the shaded region between the line OP and the curve. So we can see this shaded region very clearly. So what we need to do is remember that the area between two curves, or a curve in a straight line, is the upper curve, which is this, x e to the -2x, subtract the lower curve, or straight line, which in this case is mx, but we know that m is e to the -2, so this is really e to the -2 multiplied by x. And we need to then integrate that between the limits, which are here to here. So the x-coordinate of the lower limit is 0, and the x-coordinate of P is -1/2 ln m, but we just found out that that simplifies to 1 in the previous question. So this is the integral that we have to perform. Now the purple part of the integral is really easy because e to the -2 is a constant, so really we're just integrating x. But the pink part of the integral actually requires a little bit more work, and this has got to be done using integration by parts. So I'm actually going to do this bit separately. So x e to the -2x, we'll integrate it as an indefinite integral, and then we're not going to worry about plus c because there are limits afterwards. So remember, we need to choose one part of this to differentiate, which will be x, and we need to choose one part of this to integrate, which will be dv by dx. Now, the formula tells us that we need to do u multiplied by v minus the integral of v multiplied by du by dx, or with respect to x. So u is x. Now v is the integral of e to the negative 2x, so I haven't left a huge amount of space here for me to write this all out. So u is x, du by dx is 1, dv by dx is e to the negative 2x, and integrating that, v is e to the negative 2x, all divided by negative 2. So here, when we write down uv, we want x, but we also want negative a half e to the negative 2x, and then subtract from that the integral of v times du by dx. Now v, remember, is negative e to the negative 2x over 2. So let's simplify this. So we get negative a half x e to the negative 2x plus a half the integral of e to the negative 2x, pulling out the half and simplifying the negative negative. So negative half x e to the negative 2x minus a quarter e to the negative 2x. And we don't really need to worry about the plus c, because in a minute we're going to put in our limits. So we've integrated the pink part. It's negative a half x e to the negative 2x minus a quarter e to the negative 2x. The purple part, remember e to the negative 2 is just a constant, so it's just going to be in the answer, unaffected. Now x integrates to a half x squared, so we end up with this here. Now let's substitute in our limits. So substituting in the upper limit of 1 will give us negative a half e to the negative 2 minus a quarter e to the negative 2 minus half e to the negative 2. Now, when we substitute in the lower limit of 0, this and this will vanish, but the central term won't, and we're left with negative a quarter. So this then simplifies to give us our final answer, a quarter minus 5/4 e to the negative 2. So in this example, we have another more complex question. Let's take a look at everything we've got to do here. So first part, write down the coordinates of the intercepts of the curve with the x and y axes. So we've got this point over here, which I'll call A, and this point over here, which I'll call B. So part 1, at A, we know y is equal to 0. So 1 minus x e to the 2x is equal to 0. So either x equals 1, and then the other alternative here would be e to the 2x equals 0, but that is impossible. An exponential function cannot equal 0. So x is equal to 1. So at A, we have the coordinate 1, 0. Now B, a little bit simpler, we just know that x is equal to 0, so y is equal to 1 minus 0, e to the 0, which is just 1. So B has coordinates 0, 1. Now, part 2, find the exact coordinates of the turning point P. So this means we need to differentiate. So y equals 1 minus x e to the 2x. This is going to require use of the product rule. Here is the product. You can see that split clearly. So I'm going to call 1 minus x u, and I'm going to call e to the 2x v, and you start to see just why we have to be able to use the product rule really efficiently. So du by dx is negative 1. dv by dx, now again you're going to have to use the quick chain rule here. Differentiate that, you get 2e to the 2x, and then remember that dy by dx is equal to u multiplied by dv by dx plus v multiplied by du by dx. So that then gives us 1 minus x multiplied by 2e to the 2x, and then minus e to the 2x. Now this can be simplified if we expand the brackets and collect like terms. We can see that we get e to the 2x minus x 2x e to the 2x. So if we want to factorise again, we get 1 minus 2x e to the 2x. So we've got to find the coordinates of the turning point P. So we know that 1 minus 2x e to the 2x is equal to 0. So again, e to the 2x equals 0 is not an option. So we have 1 minus 2x equals 0, so x is equal to a half. We need to substitute that into the function f of x to find the y coordinate. So we've got 1 minus a half e to the 2 multiplied by a half, substituting into this. So that then gives me a half e. So the coordinates of P are 1/2 and 1/2 e. So part 3, we need to work out the exact area of the region enclosed by the curve and the x and y axes. So that's this region here. So that's a simple integral between 0 and 1. Now, that means we need to integrate 1 minus x e to the 2x. And this has got to be done by parts. It's a product, and one part of this does not differentiate to another part of this. So we're going to have to use the integration by parts formula to do this. So if you remember, that tells us that the integral of u multiplied by dv by dx is given by this formula here. So we need to look at our product over here, and we need to establish a u and dv by dx. So because there's an exponential part here, that's going to be the dv by dx part. U is going to equal 1 minus x, which differentiates to give us du by dx, which is -1. dv by dx will equal e to the 2x, which integrates to give us v, which is a half e to the 2x. And we're then substituting into this part first of all. So our integral, don't forget we have limits to think about later on as well, u multiplied by v, so 1 minus x multiplied by a half e to the 2x, minus the integral of v multiplied by du by dx, so that's this part here, which is the product of these parts here. So that's negative a half e to the 2x with respect to x. So substituting in the limits from the first part, we're going to get 0 for our upper limit, because 1 take away 1 gives me 0, minus a half e to the 0, which we'll deal with in a second. Now, for our integral, for the second part here, we've got minus minus and a half, so that becomes a half. And then when we integrate, we're integrating e to the 2x, which is e to the 2x over 2. And then we just need to finish off by substituting in our limits. So let's finish working through this. So this is going to give me minus a half from that first part. And then from the blue part, substituting in the limits, I'm going to get plus e to the 2 over 2, and then minus a half. So, somewhat run out of space to finish this off, but if we carry this on over here, we can see that this then simplifies to e squared over 4 minus 3/4, and then of course that's the same as the answer here if we factorise a quarter. So part 4, we're told that g of x is equal to 3f of a half x. Express g of x in terms of x. So that means we need to take f of x, which is this, and ensure that we transform it to 3f of a half x. So this 3 here is a multiplicative scale factor. Now, we're replacing x by a half x. So there's an x here, and then there's an x there. So we get 1 minus a half x, and then e to the 2 multiplied by a half x. So how does this simplify? This simplifies to 3, 1 minus a half x, e to the x. So that's what g of x is. Now, we've then got to sketch the curve y equals g of x on a copy of the graph, indicating the coordinates of its intercepts with the x and y axes and of its turning point. Now, this is more an understanding of the two transformations that have occurred here. So remember, g of x is equal to 3 f of a half x. Now, this 3 here represents a stretch in the y direction with a scale factor of 3, which means the x-coordinates stay the same, the y-coordinates multiply by 3. This part of the transformation here is a stretch in the x direction with a scale factor of 2, because it's the reciprocal of that coefficient of a half, which means the x-coordinates multiply by 2 and the y-coordinates stay the same. So overall, the two transformations can work simultaneously so that the x-coordinates multiply by 2 and the y-coordinates multiply by 3. So if we apply that to A, B and P, we can then resketch the transformed curve. So we have to remember that A has a coordinate of 1, 0, B has a coordinate of 0, 1, and P has a coordinate of a half e over 2 for the y-coordinate. So let's transform each of the coordinates. So A maps to A dash. A's x-coordinate is 1, which becomes 2, and its y-coordinate is 0, which then stays as 0. B is mapped to B dash, so its x-coordinate is 0, which then stays at 0, and its y-coordinate multiplies by 3 to 3. And P has non-zero x and y coordinates, so they're both affected, so P dash, x-coordinate becomes 1, and its y-coordinate becomes 3e over 2. So let's sketch this carefully. So A maps to A dash, which might be over here, to 0. B maps to B dash, which let's say is over here, which is 0, 3. And P maps to P dash, which is 1, which puts it at the same x-coordinate as the original A and a y-coordinate which is higher, so P dash, which is 1, 3e over 2. And then, of course, we can sketch the curve running through these points, has a similar shape to the original curve. There we go. So that is y equals g of x, and we've indicated the coordinates of the intercepts and of its turning point as well. So part 5, to finish all of this off, write down the exact area of the region enclosed by the curve y equals g of x and the x and y axes. Now, let's remember that the area for f of x was equal to a quarter e squared minus 3. Now, the x-coordinates have been multiplied by a scale factor of 2 and the y-coordinates have been multiplied by a scale factor of 3, which means that if we're thinking about area, the area will have been affected by the squares of these length scale factors. So we're going to have to multiply by 2 squared and by 3 squared to get the overall area scale factor. So this then gives us an area of 9 e squared minus 3 for the area of g of x. So the next question. We're given a curve with an asymptote and a turning point, and we've got to write down the value of a, which is where the asymptote is. Now, asymptotes occur when we get a 0 in the denominator here. So for part 1, we know that a will occur when 2x minus 1 equals 0, so x is equal to a half, so a is then equal to a half for part 1. Now for part 2, we've got to show that dy by dx is given by this result here. Now, the fact that the answer also contains y squared is a bit of a tip-off that we want to use implicit differentiation here. So, differentiating implicitly on the left-hand side, remember we currently have y cubed, so differentiating I get 3y squared dy by dx. And on the right-hand side, I've then got to differentiate this using the quotient rule. So u equals x cubed, the numerator, du by dx is equal to 3x squared, and then v is equal to 2x minus 1, dv by dx is equal to 2, and we then just need to apply the quotient rule, which I have set up ready for use here. So really easy, let's just follow it through. So we have 2x minus 1 multiplied by 3x squared minus x cubed multiplied by 2, and then all over v squared, which is 2x minus 1 all squared. Let's tidy up the numerator. So that gives me 6x cubed minus 3x squared minus 2x cubed all over 2x minus 1 squared, which then simplifies to give me 4x cubed minus 3x squared over 2x minus 1 squared. So this is the derivative of the right-hand side, remember? So I can then input that here. And then it's very obvious that all I have to do to get to the version of dy by dx in the actual question is to divide through by this factor of 3y squared. So that then gives me dy by dx is equal to 4x cubed minus 3x squared all over 3y squared multiplied by 2x minus 1 all squared, which is what we were required to get to. Now, if you don't use implicit differentiation, you're then looking at a very, very complex process to try and get to the correct answer. Now, finding the turning coordinates of the turning point P, well, we then need to set dy by dx equal to 0, which is going to help us find any stationary points. Now, that tells me that 4x cubed minus 3x squared over 3y squared 2x minus 1 all squared equals 0. Now, the only way for this to work is if the numerator is equal to 0. Factorise. Now, x equals 0 is not relevant. That's what's happening at the origin. It's not what's happening at P. So we then need to take the other alternative, which is x is equal to 3/4. And it does want the y-coordinate as well, given to 3 significant figures. So we just need to substitute into the equation here, but remember to cube root to get the final value for y. And the value for y that we should get is 0.94494 ... So 0.944 to 3SF. So let's move on to the next part of the question, part 3. So we're asked to use a substitution to transform the integral here to this integral here. So notice this is effectively the integral of y with respect to x. So we've taken this equation here and cube rooted both sides to give us the function that's being integrated. So u equals 2x minus 1, du by dx is equal to 2, and then we get dx is equal to du over 2 using the fake rearrangement. So let's take the integral that we're working out, the integral of x over the cube root of 2x minus 1, and let's start transforming it. Now, we're going to leave the x in the numerator as it is until we can deal with it in a second. The denominator then becomes u to the power of a third, and then in place of dx we can have this. Now, how do we replace this x? We go back to here, and the x hasn't cancelled out, so we have to go back to the original substitution and rewrite x as u plus 1 over 2. So bringing that into our integral. Now, the u to the 1/3, I'm going to write that as u to the negative a third. In place of x, I'm then going to have u plus 1 over 2, and then of course we've got this du and another factor of a half in the denominator. So let's pull out all the numerical constants here, so we get a factor of a quarter, and then let's multiply out the bracket effectively, so that means we get u to the power of 2/3 plus u to the power of negative a third, and that's what we're required to get to. Now, we then have to use this to find the exact area of the region enclosed by the curve, the x-axis, and the lines x equals 1 and x equals 4.5. Now remember, a was equal to 0.5, so if we're looking at x equals 1, we're going further away than that. And remember, p has an x-coordinate of 3/4, so we're a bit further away than that as well. So we're just looking at a region between 1 and 4.5 here. So that would mean our original integral would have limits of 1 and 4.5. But we need to change those limits. So if x is equal to 1, then u is equal to 2x minus 1, which is 1. So our lower limit stays as 1. If x is equal to 4.5, then u works out to be 8. So our upper limit becomes 8. So for part 3, to finish this off, we then have to perform this definite integral. And we've changed our limits, so let's go ahead. So for this first part here, u to the 2/3, we want to raise the power by 1, so that becomes u to the 5/3. Divide by the new power is the same as multiplying by 3/5. And then for the other part of this here, we've got u to the power of negative a third. We want to raise that by 1, so it becomes u to the power of 2/3. Divide by the new power, so that's the same as multiplying by 3/2. And don't forget, we've got limits of 1 and 8 to substitute in. Now, working this out, we then get a quarter. Now I'm going to input my upper limit of 8. Now 8 to the power of a third is 2, so we've then got 3/5 multiplied by 2 to the power of 5, which is 32, plus 3/2 multiplied by, well, 2, when you take 8 to the power of 2/3, we just get 4. 8 to the power of a third is 2, and then 2 squared is 4. And then we're subtracting from that. Now, when you substitute 1 in, 1 to any power is just 1, so you're just going to get 3/5 plus 3/2. Now, our calculator then gives us the result for the area, which is 231 over 40. So, in the next question, look at the graph. We've got to find the y-coordinate of the point P. So we know at P the x-coordinate is equal to pi by 3. So the y-coordinate is 1 over 1 plus cos pi by 3. And inputting that into our calculator gives us a y-coordinate of 2/3. Now, we've then got to find f dash x in part 2. So f of x is equal to 1 over 1 plus cos x. Now, we can differentiate this using the quotient rule, or we can rewrite this as 1 plus cos x all to the power of negative 1, and then I can use the quick chain rule. So f dash x tells me that this is a power function overall. The inner function is 1 plus cos x. It's being raised to a power of negative 1. So multiply by the power, reduce the power by 1, and then multiply by the derivative of the inner function. Differentiate 1, I get 0. Differentiate cos x, I get negative sine x. So this then simplifies to give me sine x over 1 plus cos x all squared. Now, hence find the gradient of the curve at the point P. So remember, at P, we know that x is pi by 3. Let's substitute that into the gradient formula. And the gradient equals 2 root 3 over 9. So we've been asked to show that the derivative of sine x over 1 plus cos x is equal to 1 over 1 plus cos x, which happens to be this equation up here. So this I would use the quotient rule for. I would set up u equals sine x, and we can differentiate that to get cos x. And then v equals 1 plus cos x, and we can differentiate that to get negative sine x. Let's then write out the quotient rule. So let's substitute into this. So we have 1 plus cos x multiplied by du by dx, so multiplied by cos x, minus u, which is sine x, multiplied by dv by dx, which is negative sine x. So that's going to effectively give us plus sine x, or sine squared x. Now this is all over our denominator of v squared, which is 1 plus cos x all squared. Let's simplify the numerator. So cos x plus cos squared x plus sine squared x all over the denominator of 1 plus cos x all squared. So remember, cos squared x plus sine squared x is equivalent to 1. So this is cos x plus 1 over 1 plus cos x all squared. And if you divide the numerator and denominator by cos x plus 1, we get 1 over 1 plus cos x. Now, what we have done is shown that if we start with sine x over 1 plus cos x and we differentiate it, then we get to 1 over 1 plus cos x, which means if we integrate 1 over 1 plus cos x, we get to sine x over 1 plus cos x using integration and differentiation as reverse processes of each other, or considering them that way. So we then have to find the exact area of the region bound by the curve, the x-axis, the y-axis, and the line x equals pi by 3. So that's this region over here. So the area is equal to the integral between 0 and pi by 3 of 1 over 1 plus cos x with respect to x, but we know that integral will give us sine x over 1 plus cos x, using essentially the reverse of what we've just done. So all we need to do is substitute in these limits, so sine pi by 3 over 1 plus cos pi by 3. Substituting in the lower limit of 0 will straight away give us a 0 because sine of 0 is 0. And this then gives us an area of root 3 over 3. Now, the last part of the question, we've got to find the inverse function, state its domain, and then add a sketch of it to the graph. So, y equals 1 over 1 plus cos x. Let's swap over x and y. So, x is equal to 1 over 1 plus cos y. Rearrange this, 1 plus cos y equals 1 over x. Cos y equals 1 over x minus 1. Y then equals arc cos 1 over x minus 1. And that's the inverse function. Now, let's think about the domain and range. So f of x, the original function, we can see its domain is that x is between 0 and a half pi. And its range, we can see that range always refers to the set of allowable y coordinates. Well, if we're between 0 and a half pi, here, that means we're between here and here on the y-axis. So that means the range is that y is between 1 and a half. So that means that the inverse function, f minus 1 of x, will have a domain that matches the range of the original function, but in terms of x, and it will have a range that matches the domain of the original function. Remember, the domain and the range swap around. So our inverse function, f minus 1x, is arc cos 1 over x minus 1, and its domain is x is between a half and 1. Now, to sketch it, of course, we want to add a line y equals x to our graph here. And we want to reflect our original function, y equals f of x, in this line. So the graph will likely look like this, with this point here being a half. Now, part 1, verify, which is a way of saying show that the x-coordinate of P is 3. So P is on the line y equals x and on the curve y equals x over the square root of x minus 2. So if x is equal to 3, let's see what happens if we substitute that into the equation of the curve. We get 3. So that suggests that 3, 3 is on the line y equals x and the curve y equals x over root x minus 2, which implies that P's coordinates are 3, 3, or P has an x coordinate of 3. We've now got to show that the derivative is given by this result here. So we are differentiating y equals x over the square root of x minus 2. So I'm going to do this using the quotient rule. I'm going to say that u equals x, which gives me du by dx as 1. And I'm going to say that v is equal to x minus 2 to the half, which gives me dv by dx is equal to a half x minus 2 to the negative a half, applying the quick chain rule. Now, let's write down the quotient rule. Then all we have to do is substitute into this very carefully. So v multiplied by du by dx, first of all, just gives me x minus 2 to the power of a half. Subtract from that u multiplied by dv by dx, over there, which gives me a half x minus 2 to the negative a half. And this is all divided by v squared, which is x minus 2, because when you square something that's at a power of a half, you just get a power of 1. Now, we've got to show that we get to the given answer, so let's divide each part of this by x minus 2. So here, first of all, remember we subtract powers, so that becomes x minus 2 to the negative a half. And then for the second part of this, we're going to get minus a half x minus 2 to the negative 3 over 2. We then need to factorise, so I'm going to take out a half, I'm going to take out the lower of the two powers of x minus 2, so that's x minus 2 to the negative 3 over 2. And then let's put in a large bracket. So for the first part, the yellow part, to multiply back we need a 2 and an x minus 2. And for the second bit, we need minus x, and that's it. So this then simplifies to give me a half x minus 2 to the negative 3 over 2, and then inside the brackets, that's x minus 4. Now, if I just rewrite this slightly, I have x minus 4 on its own in the numerator. In the denominator, I can place 2 bracket x minus 2 to the 3 over 2, which is the answer we were aiming to get to. Now, to find the gradient at P, we just need to substitute in x equals 3. So at P, we know dy by dx is then equal to negative 1/2. Now, this tells us the curve is not symmetrical about y equals x, because y equals x has a gradient of 1, and the gradient of the curve at P, if we draw in that tangent, has a gradient of negative 1/2, which means it's not perpendicular to the line y equals x, so we then don't have symmetricality. So for part 3, we're going to do an integration, and we've been given the substitution that we need to use. U equals x minus 2, du by dx is equal to 1, and then here's the fake rearrangement that we'll use for dx in a minute. Now, this integral has limits as well, so let's make sure we deal with those too. So we know that if x is equal to 3, which is our lower limit, u is equal to 1. If x is equal to 11, which is our upper limit, u is equal to 9. So our integral over here then becomes the integral between 1 and 9 of x over the square root of u, and then with respect to u. But we need to replace x, so we go back up to here, and this tells me that x is equal to u plus 2. So the x, of course, didn't cancel out, so this then gives me u plus 2 over u to the half with respect to u. I need to divide both parts of the numerator by u to the half before I can integrate, so that gives me u to the half plus 2u to the negative 1/2 du, and let's then integrate. So this becomes u to the 3 over 2, raising the power of this term here by 1. Dividing by the new power of 3 over 2 is the same as multiplying by 2/3. Now for the next one, we raise the power of this part here by 1 to give us u to the power of a half. Dividing by the new power of a half is the same as multiplying by 2, so we have a factor of 4 here, because there's already a 2 there as well. Now let's substitute in the limits, and we will see that we get 2/3. Now 9 to the power of a half is 3, 3 to the power of 3 is 27. And then we have 4 multiplied by 9 to the power of a half, which is 3. And then when we substitute in our lower limits, that's easier because 1 to the power of anything is just 1. And then simplifying this gives us the required answer of 25 to the power of 25 and a third. Now, hence find the area of the region PQR, which is bound by the curve and the lines y equals x and x equals 11. Now, we know the area here. So this is equal to 25 and 1/3. That's the integral that we have just performed. So to get the red area, we simply find the area of this trapezium and then subtract from it 25 and a third. So the area of the trapezium, the blue trapezium, is equal to a half multiplied by the sum of the parallel sides. Now, the two parallel sides are this one, which has a y-coordinate of 3, and this one, which has a y-coordinate of 11. So half the sum of 3 plus 11 multiplied by the distance between them, which is this distance here, and we know that that value is 3, so the distance between 3 and 11 is 8. So the area of our trapezium works out very simply to be 56 square units. So the area that we are after in the question, the red area, would equal 56, which is the area of the full blue trapezium, subtract the pink area that we found via integration, which is 25 1/3, and this then leaves us with an answer of 92/3 square units.